Thank you, Saurabh. So, am I audible? Yeah. So, I thank the organizers for inviting me to this conference. So, the title of my talk is Zeros of L function attached to half integral with modular form. We'll see that how some properties like usual L function we study some of the properties are different in this case. In the case of half integral with modular. Okay, so the talk is about zeros of L function attached to half integral with modular form. So we begin with a Riemann zeta function. So this is usual Riemann zeta function we know, and for real part of S bigger than 1 we have Euler product, and this is the definition. And we know that this is non-zero for real part of S bigger than equal to 1. So in fact, real part of S exactly equal to 1 gives you prime number theorem. And it also satisfies certain this kind of equation that is called functional equation. So S is related to 1 minus S with some gamma factor and pi factor. Okay. So, so if we look at the zeros of Riemann zeta function, that we get trivial zeros on real line for real part of S less than equal to 0. So on the real line they lie. And except those zeros, it does not vanish any other place in the real part of S less than equal to 0. So now the question is, so the all whatever remaining zeros, they belong in that strip, that is particle strip. And the Riemann hypothesis, as everybody knows possibly, that it says that all the zeros should lie on real part of S equal to half. And but as everybody knows that it is not solved yet, so it is not known, but there are more advanced result known. But the first attempt, but first result in this direction was due to Hardy in 1914. So he proved that there are infinitely many zeros on this line, real part equal to half. Now, so mostly I'll discuss about this method, how the Hardy has used in case of Riemann zeta function, because many people have used the method of Hardy in different cases, different L functions. So what Hardy did, so Hardy constructed a function which now we call as Hardy function. So this is Hardy function in the case of Riemann zeta function. And what is useful, what property it has? So the property it has is that first is that it is a real valued function. So once it is a real valued function and we have this, trivially one can see that this is true, that the absolute value of Riemann zeta function at half plus it is same as zt. Okay, so zt is real valued function. So from here one can say that this is 0, zt is 0 if and only if zeta half plus it is 0. Okay, so this is important because zt is real valued function, we are relating it to Riemann zeta function. And now what do we do here? So what Hardy did is, this is real valued function. So real valued function, so you look at the number of sign changes. So if you have one sign change, so that means at one point if it is positive, another point it is negative, so there is a 0 in between, because this is, you can see that this is continuous function, etc. Okay, so this is the idea, very simple idea, just detect sign change and then you do that. But idea is simple, but one has to work out. And as I said, that the idea is to study the sign changes. So that means ultimately the aim is to prove that there are infinitely many sign changes for zt. And once infinitely many sign changes for zt, so this will imply that infinitely many zeros for zt, and this will imply that we have infinitely many zeros for zeta function on the real part as equal to half. Okay. So this is the so how to prove that there are infinitely many sign changes. So you look at you for sufficiently large t, just you prove that there is exactly one sign change between t and 2t. So once you have one sign change in t to 2t, then this will imply that infinitely many sign changes because sufficiently large t. So then you can take 2t to 40, 40 to 80 like that, and then you get infinitely many. Okay, so now this is the idea that if zt is of same sign, that means you are proving by contradiction that you want to prove that there is one sign change. Suppose it is not the case, then this holds. Okay, because no sign change means like this is both are same. And now, how he got a contradiction? He got a contradiction by proving that this is bigger than t, whereas this is less than t power alpha for some alpha less than 1. Okay, and this will give you a contradiction because if there is no sign, then this should hold, but you are getting lower bound is bigger and then upper bound is smaller. So this will give you a contradiction. And this is the idea. Idea is very simple, but of course you have to do all this calculation that how to get this lower bound. Upper bound is relatively easy, but lower bound also sometimes it depends on which L function you are considering. So sometimes this may become difficult and sometimes the other one. Okay, so now I come to the half integral weight case. So I'm not giving any definition, etc. But suppose we consider this space Sk plus half, k is integer, level is 4n. This is the space of cos form of weight k plus half on the group gamma 0 4n. And note that whenever we are considering half integral weight modular form, so always level should be divisible by 4. So we know the theory in this case only. So that is why always half integral case weight case means the level should be divisible by 4. That is why I have taken 4n. So now I first state some of these properties of the L functions attached to half integral weight modular form or cusp form. Mostly we will consider cusp form because the L function in that case is analytically continued. If it is not a cusp form, then you have a certain singularity. And then after that, we'll look at the Hardy's method, how we can do in this case. Okay, so one more thing is that in between I have not said anything about what happens in case of integral weight modular form. So much more results are known, and then there is a difference between half integral and integral weight. So I'll come to that. So so the L function, any modular form, in fact, you have a Fourier series expansion, and then you consider the L series is defined, just you consider the coefficient and then consider the Dirichlet series attached to that. So this is the Dirichlet series or L series attached to the half integral weight modular. And as we know, this is well known that this is analytically continued to the whole complex plane, and we have some kind of functional equation. Not exactly in the case of Riemann zeta function, if you look at that, S is related to 1 minus S. And here, of course, this is not 1, this is k plus half here we get, but the other side we get F slash W4n. So what is W4n? So this acts on F like this. So this is again, so F is a half integral weight modular form. So again, F slash W4n is also a half integral weight modular form. Okay, if F is a cusp form, again this is also a cusp form. Okay, so this is what we have in this L function. Now, so this study actually was started, the study of the zeros of half integral weight cusp form L function attached to half integral with cusp form. This was started by Yoshida. So what he did, he was computing the zeros of L function. So he considered many examples. I am just giving one example here. What is the half integral with modular form? So for that, this is the theta function we know, usual theta function. This is in fact a modular form of weight half on gamma 04. And we have Dedekind's eta function. This is also, it also satisfies some kind of transformation property. And if we consider GZ is this one, and this is a cusp form of weight 9/2. So half integral weight, and this is on gamma 04. This group is gamma 04, and the dimension of this space is 1. So this generates this space S 9/2 gamma 04. Okay, so what we have in this case, that like we are considering, we are in gamma 04. So the free K involution, whatever I said, so in this case it will be W4. And in this case, this is same, like it maps, and then so it has to also it is some kind of involution. So it takes eigenvalue plus or minus 1, and in this case this is dimension 1, etc. So this gives you this is 1. So G/W4 is G, and so it satisfies this functional equation, because if you look back this functional equation, that was G/W4, and in this case this is G, so we get this. Okay, and Yoshida computed some of the zeros of this function, and he proved the existence of zeros outside the critical strip. So he proved that there are zeros outside the critical strip also. Like in case of Riemann zeta function, it was not the case. So except for trivial zeros, there is nothing outside. But in this case, there are zeros which lie outside the critical strip. So that means the Riemann hypothesis is not true. So it says that the Riemann hypothesis is not true in this case. Okay. Okay, so Riemann hypothesis is not true. Riemann hypothesis says that you have all the zeros on the half line. So in this case, it will be not exactly real part of S equal to half, because how do you get the half line? Because you get from the functional equation. So there it was S relating to 1 minus S. So that means this was the half. 1/2 means 1 minus S. So 1 is there. So here it S related to K plus half. So the half line will be K/2 plus 1/2. So Riemann hypothesis is not true, but still can we expect that still we have infinitely many zeros on that half line? And one of the reasons that it has the Riemann hypothesis is not true is that it has no Euler product. If you take eigenform, etc., Euler product is not there in this case. So that is the reason. So mostly people say that if you do not have Euler product, that you cannot expect a Riemann hypothesis. And in this case, this is the case. So now the question which I asked, that do we have infinitely many zeros of, at least for this example, on the critical line? And this is in fact true. In fact, we prove a more general result, that if we take, so this is a joint work with Pujari and Srinivas. So if we take a so if we take a cusp form on gamma 04, which is an eigenform for all Hecke operators and operator W4, because we want that F/W4. If you look at the Riemann zeta function, Riemann zeta S relating to zeta 1 minus S. But if you get different one, F/W4 is something different, then similar idea we cannot use. So that is why we have this condition also. And also another condition is that the coefficient, Fourier coefficients are either all are real number or all are purely imaginary numbers. Okay, this is required because like Hardy, what he did, he considered a function which is real valued. So for that function to be real valued, we need this. We have a functional equation, and from there you deduce that the function should that Hardy function should be real valued, and for this we need this too. And we have proved that then there are infinitely many zeros of this L function attached to that alpha on that critical line. Okay, in particular, whatever G we have, G satisfies all these conditions, and so G has the L function attached to G has infinitely many zeros on the critical line. Okay, so what is the idea? Again, I'll give some idea of proof. Again, the method is same Hardy's method, but here there are many things count because there Riemann zeta function all coefficients are 1, so many things you trivially, but here you need to estimate certain things. And like in the Riemann zeta case, here also we do like this, and then we consider the Hardy function here, and using similar that this is absolute value is 1, so this is 0 if and only this Hardy function at t is 0, and we consider the integral I1 and I2 and get a contradiction like the previous case. And to get a lower bound, we use some more general result due to Ramchandra, which gives a lower bound that I2 is bigger than 2. And for upper bound, we use, I think, well-known estimates, but not very difficult, but you need to estimate certain exponential integral and exponential sum. So to estimate this, what we do, we move the line of integration. So why we move? Because we want to use the Dirichlet series expression, because on this line we cannot use the Dirichlet series expression of LSF because it is not absolutely convergent in that. So we move it so that we can use the Dirichlet series expression. And then if we move that, then we get contribution, the horizontal contribution J1 and J3. And this is what J1, J2, J3. So yes. So the J1 and J2, one can easily estimate. It is not difficult to estimate. So the other one, the J2, we use the Dirichlet series expression, and we estimate certain exponential integral and exponential sum to get that this is a small o of t. And so if we club everything together, then we get that I1 is small o of t. And like in the previous case, that we are getting lower bound bigger than t, and this is upper bound is small o of t, so they give contradiction, and so we have sign change in that, and so we have one sign change and 1 0 in that t2 2t, and then ultimately we have infinitely many zeros. So idea is simple, but if you look at this idea, one may want to use in other kind of L function. People have used most of the cases whenever they study zeros of L function, somehow they use variant of Hardy's method or some, because more improved results are known in L functions. So they use somehow Hardy's method, variants of Hardy's method. Okay. So this is for gamma 04. If you look at the result I stated was for gamma 04. So what about higher level? Modular form of half integral one can define for 4n. N is any integer. We consider this case when n is 1. The result I stated was when n is 1. Now this is the again improve the result. We generalize it to gamma 04n, where n is a perfect square. So again, the reason for n is a perfect square is again f/w4n. So that is a cusp form, if n is not perfect square, so that is a cusp form, but it will not lie in this same space. It will not be xk plus half gamma 0 4n. It will be with some character, gamma 0 4n with some character. So if that is the case, then we cannot apply Hardy's method again, because we want to construct Hardy's function and etc. And then we want real valued Hardy's function. So all these things we cannot do if the level is arbitrary. If perfect square, then it is true that W4n will map f to another element in that space, sense space. Okay, so here we generalize it to 4n, and another kind of generalization is we prove it for this L function. So this LSF plus minus, either plus you take or minus. So this has infinitely many zeros on the critical line. And as a corollary, we get similar result, that assume all the hypotheses, whatever here we have in this theorem. And if it is plus minus f, either f or minus f, then if you substitute here, you get that LSF has infinitely many zeros on the critical line. So why we were not able to do this in the previous case was we don't use exactly the method of Hardy. So we use some variant of Hardy's method. So this was first done by Wilton. So Wilton considered the L series attached to Ramanujan's tau function, and he used some kind of variant. So although it is not there, also here also you have to consider two kind of integral, and then you need to get a contradiction by having lower bound and upper bound. So in this case, getting a lower bound is difficult. Yeah, so whatever in this previous case, I think getting upper bound was little bit of work you have to do. Here, getting upper bound was okay, but getting lower bound was difficult here in this case. Okay, and so this method, although means like you can relate the previous method and this method also, but this is some kind of variant you can say, because similar integral we are considering, and then we are getting lower bound and upper. So everywhere actually, if you are counting zeros, every time you are using somehow Hardy's method or a variant of Hardy method. Okay, so with this I stop.
Thank you very much for the nice talk. There are questions from the audience. Yeah, please. Is it working?
Yeah. Yeah, so there are also refinements of Hardy's method where they get, a positive density of zeros.
Yes.
Like in T2, 2T,
Yes.
they get a positive density.
Yes.
So I was wondering whether there is any hope for doing those in this setting.
In this setting, yes, that is all methods, if you look at, they use Euler product.
Okay.
Somehow prime will come into the picture. So here we do not have Euler product. So that kind of thing we cannot, at least whatever method we have, we cannot use in this case.
Okay, so those ones which use positive, which have positive density are using the Euler product.
Yes, yes, all the methods. Any method you can use, those who have proved positive proportion, they use Euler product. Prime comes to the picture somehow.
I see. Okay, okay, thanks.
Hello. Yeah.
Yes.
So, what is the current state of knowledge when you consider GL and L functions? Because there you have everything, right?
You do not have everything. So another thing I didn't mention is that so Riemann zeta is degree 1 L function. Modular form of integral weight is degree 2, and this half integral weight also degree 2. Beyond degree 2, nothing is known. Even infinitely many is not known. Because as I said that exponential sum, etc., this is difficult to estimate, because whatever expected thing we want, those things are not known. So in fact, nothing is known.
Are there further questions?
This half integral weight does not have any Euler product.
Yes.
So how you define degree here?
Degree, you do not need to have the Euler product. No, you define with respect to this gamma factor. That if you look at the Selberg class, etc.,
Two
that
times
is.
coefficient.
Yeah.
Could you maybe please explain again why you need it to be eigenfunction of the Frick involution as well?
So the first result.
Yeah, I mean, in all of
Yes.
these-
So what happened? We use certain analytic methods, which at that time, this is the old result 17. So at that time, it was available for gamma 0, 4 and Hecke eigenform. Just we use that and then we get it. But the later case, we do not need Hecke eigenform. Only for it is f/w4 that should be either +1 or -1. That we need to get the Hardy's function so that it will take real value.
Thank you.
What about zeros of like Mach modular forms and?
So there has to be L function first attached to that, because Mach modular form, when you take the coefficients, I think grow exponentially. Here the coefficients, they are polynomially bounded with respect to n.
So which kind of exponential sums do you get?
Usual an e power 2 pi, just usual
So-
one we get. E
Yeah,
power-
so how does the function look like? Amplitude function, how does it
Or
look?
Fn, how is e to the power 2 pi Fn? So what is the Fn kind? It's a degree polynomial or some?
Not polynomial, just n or I think it was.
And to the power 2 by
Yes.
3 for degree 3.
2/3.
Yeah.
But degree 3.
Or attached to
Here, no, here one needs to see. I do not remember, but
It's type alpha n to the beta, something like that.
yes, something kind of it comes. Whatever in the integral weight case, similar we get here.
Okay.
But I do not remember exactly what that exponential sum.
Yeah, and in the degree 3 case, it's too hard.
2 by 3. Yeah, 2 by 3.
Yes, okay. Okay, are there other questions? If not, then let's thank the speaker again.